The year is 1943. On a secret testing ground somewhere in the English countryside, a group of high-ranking British Army officers are standing in a muddy field, staring at a machine that looks less like a weapon of war and more like a mechanical nightmare brought to life. It is a low, tracked vehicle, squat and angular. But as the officers watch, the machine begins to change shape. With a hydraulic whine, a long, armored neck rises from the chassis, lifting a small, enclosed pod into the air. It climbs higher and higher until it towers 11 feet above the ground. Inside that pod, lying face down in a prone position, are two men. They are suspended in the air, peering through narrow slits, their hands gripping the controls of twin machine guns. The silhouette is unmistakable. It looks like a giant steel insect rearing back to strike. The name given to this creation is as strange as its appearance: the Praying Mantis. At first glance, it is easy to dismiss the Praying Mantis as one of those bizarre, eccentric failures that litter the history of military engineering. A mad scientist invention with no place on a serious battlefield. But to dismiss it as merely ridiculous is to miss the profound tragedy hidden within its gears. This machine was not built by a madman. It was not built by a fool. It was built by a man who was trying desperately to solve a problem that had haunted him for 25 years. The Praying Mantis is not just a tank. It is a physical manifestation of trauma. It is an engineering answer to a question asked in the blood and mud of 1916. And its failure tells us something vital about how wars are fought, how memories shape technology, and how sometimes the most brilliant solution is worthless if it solves the wrong war. This is the story of a machine designed to save lives by hiding them, and why it ultimately became a footnote in history, not because it didn't work, but because the world had moved on without it. To understand the Praying Mantis, we have to leave 1943 and go back to the trenches of the First World War. We have to understand the geometry of that conflict. For 4 years, millions of men lived in a world defined by a single, brutal rule. If you show your head, you die. The trenches were typically about 6 to 7 feet deep. As long as a soldier stayed below the parapet, the wall of earth and sandbags at the top of the trench, he was relatively safe from direct fire. But to fight, to observe the enemy, or to fire a weapon, he had to expose himself. This created a blind zone above the trench line. The moment a soldier stood on the fire step to look over the top, he entered the kill zone. German snipers and machine gunners were waiting, their weapons trained on the parapet line, watching for movement. The vast majority of infantry casualties in trench warfare occurred not during the grand charges across no man's land, but in these small, daily moments of exposure. A man would lift his head to check a noise or to fire a rifle grenade, and a sniper's bullet would find him instantly. This reality created a deep psychological scar on the generation that survived it. They learned, instinctively and painfully, that vertical exposure equals death. The safest place was low to the ground. The ideal soldier would be invisible, able to see and kill without ever lifting his head above the dirt. One of the men who survived this trauma was Ernest Tapp. Tapp was a veteran of the Great War, a man who had seen friends die simply because they stood up at the wrong moment. After the war, he became a successful engineer and co-founder of County Commercial Cars, a company known for building robust, specialized vehicles. But the memory of the trenches never left him. Tapp became obsessed with a single idea: how to decouple firepower from exposure. In traditional warfare, a soldier's eyes and his weapon are always together. To shoot, you must see. To see, you must expose your head. Tapp wanted to break this link. He wanted to build a machine that could lift the weapon and the eyes into the danger zone while keeping the body of the soldier safely hidden below. This is where we must introduce the concept of battlefield geometry. Every war has a dominant geometry. In the First World War, the geometry was vertical. The struggle was about height. Who could see over the ridge? Who could dominate the high ground? Who could shoot over the trench wall without getting shot back? Tapp's mind was locked into this geometry. He saw the next war as a continuation of the last one. He imagined a battlefield where static lines of infantry faced each other across a deadly no-man's land, where survival depended on being able to fire from behind cover. He didn't foresee the blitzkrieg. He didn't foresee the sweeping armored movements of 1940. He saw 1916, but with better machines. So in the late 1930s, as Europe began to slide toward war once again, Ernest Tapp went to his drawing board. He began to sketch a vehicle that would solve the problem of the sniper. A vehicle that could crawl on its belly like a soldier, then raise its head to fire and vanish again before the enemy could react. He was designing a mechanical answer to a human fear. And in doing so, he was about to create one of the most unique and ultimately tragic machines in the history of armored warfare. Ernest Tapp's core idea for the Praying Mantis was simple, elegant, and on paper, absolutely brilliant. The concept centered on a low-profile, tracked chassis, something small enough to hide behind a hedgerow or a low wall. But the genius lay in the weapon system. Instead of a fixed turret, Tapp envisioned a hydraulically powered boom that could raise a small, armored fighting compartment high into the air. This design allowed the vehicle to remain completely concealed while its head, containing the machine guns and the operator, peered over obstacles. It could shoot from behind a wall without exposing the rest of the tank. It could lift its weapons over the parapet of a trench, fire a burst, and then instantly retract back down into safety. The tactical potential seemed enormous. Imagine a city street where an enemy sniper is pinned down on a second floor. A normal tank would have to drive out into the open to engage him. The Praying Mantis could simply park behind a pile of rubble, raise its head, and fire directly into the window without ever showing its hull. Or consider a defensive line where infantry are dug in. The Mantis could act as a mobile pillbox, popping up to suppress an attack, and then dropping down to reload or reposition. In the late 1930s, this kind of thinking was very much in vogue. The British Army, like many others, was still grappling with the lessons of the First World War. There was a genuine fear that the next conflict would bog down into another static stalemate. If that happened, a vehicle that could dominate no man's land without exposing its crew would be invaluable. The strategic anxiety of the time played a major role. As rearmament began in earnest, military planners were looking for ways to break the deadlock of trench warfare. They remembered the slaughter of the Somme and Passchendaele. They wanted machines that could save lives. Tapp's design promised exactly that. It offered a way to fight an offensive war with defensive safety. However, moving from concept to reality is where the trouble began. The first prototype of the Praying Mantis was built not as a fully armored vehicle, but as a proof of concept machine. And immediately, it revealed a critical flaw that no amount of engineering could easily fix: the human body. Tapp's initial design called for a single operator. This man would lie prone inside the vehicle's hull, controlling both the driving and the weapon system. To fire, the operator would use a set of controls to raise the boom. But here was the problem. As the boom went up, the operator went up with it. The design constraints required an ultra-low silhouette. This meant there was no room for a seated crew. The driver had to lie on his stomach, looking out through a periscope or a slit. When the boom was raised, his entire body was lifted into the air, suspended at an angle. This created a physiological nightmare. When a person lies flat, blood pools evenly throughout the body. But when that person is suddenly tilted upward at a sharp angle, gravity takes over. Blood rushes to the feet, leaving the brain starved of oxygen. Conversely, if the angle is reversed, blood rushes to the head. the single operator was tasked with an impossible workload. He had to drive the vehicle over rough terrain, control the hydraulic lift, observe the battlefield, aim the weapons, and fire, all while lying in a position that was physically exhausting. The strain on the neck muscles alone was immense. To see forward, the operator had to crane his neck back constantly. After just 10 or 15 minutes, fatigue would set in. The military trials of this first prototype were a disaster. Officers found it nearly impossible to operate the vehicle for any extended period. The cognitive load was too high. The physical discomfort was too great. The vibration of the engine, transmitted directly through the prone body, caused disorientation and nausea. This failure highlights a critical concept in military design: human factors engineering. In the 1940s, this science was still in its infancy. Most tanks were designed around the mechanical requirements of the engine and the gun, with the crew fitted in wherever there was space. But usually, the crew sat upright. Their bodies were in a natural, stable position. The Praying Mantis inverted this. It forced the human body to conform to a mechanical necessity that was biologically unsustainable. Tapp had solved the problem of vertical exposure, but he had created a new problem of human endurance. He had built a machine that could hide, but he had forgotten that the man inside still had to function. The rejection of the single-crew prototype should have been a warning sign. It should have suggested that perhaps the entire concept was flawed. But Tapp was not deterred. He believed the problem was simply one of workload. If one man couldn't do it, perhaps two men could. And so he went back to the drawing board, determined to make his mechanical insect work, even if it meant defying the laws of physiology. Ernest Tapp's next move was to split the workload. The single operator concept had failed not because the machine couldn't lift its head, but because the human inside it couldn't survive the strain. So, Tapp designed a two-man version of the Praying Mantis. This new prototype would have a driver and a gunner, both lying prone in the hull, side by side. The base platform for this new machine was the Universal Carrier, the ubiquitous tracked vehicle of the British Army. Known for its reliability and mass production, the Universal Carrier was powered by a Ford V8 engine and had already proven itself on battlefields from North Africa to Europe. It was a sensible choice. Over 110,000 of them would eventually be produced during the war. If the Mantis concept worked, it could be easily integrated into existing supply chains. The armament was also upgraded. Instead of a single machine gun, the new prototype featured twin Bren light machine guns mounted in the elevating pod. This wasn't heavy firepower. It wouldn't stop a tank, but it was enough to suppress infantry and take out snipers. The idea was to create a mobile pillbox that could pop up, fire a burst, and disappear. But as Tapp built this second prototype, he ran headfirst into a problem that no amount of ingenuity could solve: physics. When you raise a heavy object high into the air on a narrow base, you change the center of gravity dramatically. The Universal Carrier was a stable vehicle when it was low to the ground, but when the Mantis raised its weapon pod to a height of 11 feet, it became a pendulum. The slightest bump in the terrain was magnified. A small tilt of just 2 degrees at the base translated into a massive sway at the top of the boom. This is the physics problem. The hydraulic lift system was strong enough to raise the pod, but it wasn't designed for dynamic lateral stabilization. As the vehicle moved over uneven ground, the pod would oscillate back and forth. The gunner inside the pod was subjected to a constant, nauseating motion. It was like trying to aim a rifle while sitting on a swing. The field trials were brutal. The gunner reported severe motion sickness almost immediately. The swaying made accurate fire impossible while moving. And even when stationary, the slightest adjustment of the controls caused the pod to jerk. The physical strain on the crew was immense. They were lying prone, their bodies subjected to the vibrations of the engine and the swaying of the pod. After a short period, they would be exhausted, dizzy, and unable to fight effectively. Moreover, the elevated position created a new kind of vulnerability. While the low hull was hidden, the raised pod was a beacon. It was a target. And because the armor on the pod was thin, designed to save weight, it offered little protection against anything heavier than small arms fire. A single well-placed shot from an anti-tank rifle or a cannon could decapitate the Mantis. This brings us to the tactical reality check. By 1943, when the second prototype was being tested, the nature of warfare had shifted dramatically. The static lines of World War I were a distant memory. The Blitzkrieg had demonstrated the power of mobility, speed, and combined arms. Armies were moving fast, punching through defenses with tanks and mechanized infantry, supported by close air support and artillery. The British Army was preparing for the invasion of Normandy. Their focus was on funnies, specialized engineering tanks designed to clear obstacles, bridge gaps, and destroy bunkers. These were vehicles like the Churchill AVRE, with its massive mortar for smashing concrete, or the Sherman Crab, with its flailing chains to detonate mines. They were tools for breakthrough, not for static observation. The Praying Mantis was a solution to a problem that no longer existed. In 1916, the sniper was king. In 1944, the tank was king. A machine that could pop up and shoot over a wall was useful in a trench stalemate, but in a fluid battlefield, where tanks were maneuvering at 30 miles per hour and aircraft were strafing columns, the Mantis was a liability. It was slow, lightly armed, and mechanically complex. The concept of doctrinal drift is crucial here. Technology must always match doctrine. Tapp had built a machine that perfectly matched the doctrine of 1918: static defense, observation, and localized suppression. But by 1944, the doctrine was maneuver warfare. The Mantis simply didn't fit. It was a dinosaur in a world of mammals. The cost-benefit analysis was clear. On the positive side, the Mantis offered a unique capability: the ability to fire from complete cover. It had a low silhouette when retracted, making it hard to spot. It was an innovative concept that pushed the boundaries of what a vehicle could do. But the negatives were overwhelming. The mechanical complexity of the hydraulic system made it prone to failure in the field. The ergonomics were a disaster, leaving the crew exhausted and sick. The armor was weak. The firepower was limited to machine guns, useless against enemy armor. And most importantly, it was a specialized tool in a war that demanded flexibility. In 1944, the British war economy was stretched to the limit. Factories were churning out Shermans, Cromwells, and Churchills. There was no spare capacity for experimental oddities. The focus was on mass production of proven designs. The Praying Mantis was an interesting idea, but it was an idea whose time had passed before it was even born. The project was quietly canceled. The prototypes were scrapped or stored. Tapp's dream of saving lives by hiding them ended not with a bang, but with a bureaucratic decision. The war moved on, leaving the Praying Mantis behind as a curiosity, a footnote in the history of armored warfare. But the story doesn't end there. Because while Tapp may have failed to build a practical weapon for World War II, his core idea, separating the gun from the exposure, wasn't wrong. It was just waiting for the right technology to make it work. The failure of the single-operator concept was not just a technical setback. It was a profound warning sign about the interaction between human biology and machine design. When Tapp conceived the Praying Mantis, he envisioned a seamless integration of man and metal. The operator would be the brain, the machine, the body. But in practice, the body revolted against the machine. The primary issue was the prone position itself. Lying flat on your stomach for extended periods is unnatural for tasks requiring fine motor control and high alertness. The human body is designed to be upright or seated when operating complex machinery. In a prone position, the neck must be constantly craning upward to see forward. This hyperextension of the cervical spine leads to rapid fatigue and pain. Within minutes, the operator's ability to concentrate degrades. Furthermore, the vibration of the engine was transmitted directly through the hull to the operator's chest and stomach. In a seated position, the spine acts as a shock absorber. In a prone position, there is no such dampening. The result was a constant, jarring shaking that made precise control of the hydraulic lift nearly impossible. The operator was fighting the machine just to stay steady. Then there was the issue of cognitive overload. A single man was expected to drive the vehicle over rough terrain, manipulate the hydraulic controls to raise and lower the pod, scan for targets, aim the weapon, and fire, all while lying face down in a cramped, noisy, vibrating metal box. It was simply too much for one brain to process. The mental workload exceeded human capacity. When the military testers reported their findings, they were unequivocal. The single-crew Mantis was unusable. The operator would become exhausted and ineffective long before he reached the battlefield. The project was rejected in its current form. But Tapp was not ready to give up. He believed the concept was sound, even if the execution was flawed. He reasoned that if one man couldn't handle the workload, two men could. And so he went back to the drawing board, determined to make the Mantis work. Tapp's solution was the two-man version of the Praying Mantis. By splitting the roles of driver and gunner, he hoped to reduce the cognitive load on each crew member. The new prototype was built on the chassis of the Universal Carrier, a proven and reliable platform. It was powered by a Ford V8 engine and armed with twin Bren light machine guns. This second iteration addressed some of the ergonomic issues, but it introduced a new, critical flaw: physics. The fundamental problem with the Mantis design was its high center of gravity when the weapon pod was raised. The Universal Carrier was a stable vehicle when its weight was low to the ground. But when the Mantis lifted its heavy armored pod 11 feet into the air, it became top-heavy. The base of the vehicle was narrow, and the lever arm created by the raised boom magnified any movement at the chassis level. Imagine holding a heavy weight at the end of a long pole. A small twitch of your hand causes the weight to swing wildly. This is exactly what happened to the Mantis. As the vehicle moved over uneven ground, the slightest bump or dip caused the pod to oscillate violently. The hydraulic system, while powerful enough to lift the pod, was not sophisticated enough to provide dynamic lateral stabilization. It could raise and lower the boom, but it couldn't stop it from swaying side to side. Field tests confirmed the worst. The gunner in the raised pod experienced severe motion sickness almost immediately. The swaying made aiming impossible while on the move. Even when stationary, the slightest adjustment of the controls caused the pod to jerk and shudder. The crew reported feeling dizzy and nauseous after just a few minutes of operation. Moreover, the elevated position made the Mantis highly vulnerable. While the low hull was hidden, the raised pod was a distinct target. Its thin armor offered little protection against anything heavier than small arms fire. A single hit from an anti-tank rifle or a cannon would be catastrophic. The physics of the design were simply incompatible with the requirements of a combat vehicle. Tapp had built a machine that could lift a gun, but he hadn't built a stable platform to fire it from. By 1944, the nature of warfare had evolved far beyond the static trench battles of 1916. The German Blitzkrieg had demonstrated the power of mobility, speed, and combined arms. Armies were no longer bogged down in stalemates. They were maneuvering across vast distances, punching through defenses with tanks and mechanized infantry. The British Army was preparing for the invasion of Normandy. Their focus was on funnies, specialized engineering tanks designed to clear obstacles, bridge gaps, and destroy bunkers. These were vehicles like the Churchill AVRE and the Sherman Crab, tools for breakthrough and momentum. In this context, the Praying Mantis was an anachronism. It was designed for a war of observation and localized suppression, a war that had ended 25 years earlier. In the fast-paced, mobile battles of 1944, a slow, lightly armed vehicle that had to stop to fire accurately was a liability. The concept of doctrinal drift explains why the Mantis failed. Technology must align with doctrine to be effective. Tapp's design aligned perfectly with the doctrine of 1918, but it was completely out of step with the maneuver warfare doctrine of 1944. The cost-benefit analysis was clear. The Mantis offered a unique capability, firing from cover, but the mechanical complexity, ergonomic failures, weak armor, and limited firepower outweighed any advantage. In a total war economy, there was no room for such specialized, flawed experiments. The project was canceled. Tapp's dream of a machine that could save lives by hiding them was over. The Mantis was relegated to history as a curiosity, a testament to the dangers of designing for the last war. The tragedy of the Praying Mantis is not just that it was mechanically flawed, but that it was born into a world that no longer needed it. By 1944, the British Army was not preparing for another stalemate on the Somme. They were preparing for the liberation of Europe, a campaign of rapid movement, hedgerow fighting, and mechanized thrusts. The doctrine had shifted from the static attrition of World War I to the fluid maneuver warfare of World War II. In this new reality, a vehicle designed to peek over a wall and fire machine guns was a tactical orphan. The battlefield was dominated by the tank, the Sherman, the Cromwell, the Churchill. These were machines built to punch through enemy lines, to duel with panzers, and to exploit breakthroughs. They were mobile fortresses, armed with high-velocity cannons and thick armor. They didn't need to hide. They needed to move. The British funnies of the 79th Armored Division, Hobart's specialized tanks, were the true innovations of the era. The Churchill AVRE, with its dustbin mortar, could smash concrete bunkers. The Sherman Crab could flail a path through minefields. The Crocodile flamethrower could clear trenches. These were tools designed to remove obstacles so the main force could keep moving. They solved the problems of 1944, mines, bunkers, anti-tank ditches. The Praying Mantis solved the problem of 1916, the sniper in the trench. It was a brilliant answer to a question that nobody was asking anymore. Consider the timeline. In World War I, the sniper was king because movement was impossible. In World War II, the sniper was a nuisance, but artillery and air power were the killers. If a German machine gun nest held up an advance, you didn't need a mechanical insect to peek over a wall and duel with it. You called in a mortar strike, or you flanked it with a tank, or you suppressed it with overwhelming fire. The intricate game of cat and mouse that Tapp envisioned had been replaced by the sledgehammer of combined arms. This is the concept of doctrinal drift. Military technology does not exist in a vacuum. It must serve the prevailing doctrine of the time. The Mantis was a mismatch. It was a defensive weapon in an offensive war. It was slow and methodical in a conflict that rewarded speed and aggression. When the British War Office looked at the Praying Mantis in 1944, they had to make a cold calculation. Was this machine worth the resources to build, train crews for, and deploy? On the plus side, the Mantis offered a unique capability. No other vehicle could fire from complete cover while remaining hidden. Its low silhouette, when retracted, made it incredibly hard to spot, ideal for ambushes or reconnaissance. It was an innovative concept that pushed the boundaries of what an armored vehicle could be. But the negatives were overwhelming. First, there was the mechanical complexity. The hydraulic system required to lift the pod was intricate and prone to failure in the muddy, gritty conditions of a battlefield. If the hydraulics failed, the pod would be stuck in the raised position, a sitting duck, or collapse, potentially injuring the crew. Second, the ergonomics were a disaster. The crew was exhausted and sick after just minutes of operation. A weapon that incapacitates its own operators is useless. Third, the armor was dangerously thin. To keep the weight down so the hydraulics could lift it, the pod was lightly armored. It could stop rifle bullets, but anything heavier, a 20mm cannon, an anti-tank rifle, shrapnel from a nearby explosion, would tear right through it. In a war where high-velocity anti-tank guns were everywhere, the Mantis was a death trap. Fourth, the firepower was limited. Twin Bren guns were fine for suppressing infantry, but they were useless against enemy armor or fortified positions. The Mantis could annoy the enemy, but it couldn't destroy them. Finally, there was the situational usefulness. How often would a commander actually need a vehicle that could shoot over a 10-foot wall? Maybe in a specific urban combat scenario, or a rare defensive setup. But for the vast majority of missions, advancing across open country, clearing woods, supporting infantry, a standard tank or armored car was far superior. In 1944, the British war economy was running at full tilt. Factories were churning out thousands of Shermans and Cromwells. Every ton of steel, every engine, every hour of labor had to be justified. There was simply no room for a specialized, flawed experiment that might be useful one of the time. The decision was inevitable: cancel the project. The prototypes were scrapped or put into storage. Ernest Tapp's vision of a safer way to fight was consigned to the scrap heap of history. But the story of the Praying Mantis is not just about a failed tank. It is a lesson in the dangers of fighting the last war. It shows us that innovation without context is just engineering. And sometimes, the most brilliant ideas are the ones that arrive too late, or too early. Ernest Tapp's Praying Mantis is often remembered as a failure, a curious footnote in the history of armored warfare. But was he truly wrong? Or was he simply ahead of his time? When we look at modern battlefields today, we see echoes of Tapp's vision everywhere. Remote weapon stations, RWS, allow gunners to fire from inside the safety of an armored vehicle. Mast-mounted sensors on reconnaissance vehicles can peek over hills and walls without exposing the hull. Pop-up missile systems hide behind cover until the moment of launch. Tapp's core concept, separating the eyes and the weapon from the vulnerable body of the vehicle, was sound. He correctly identified that direct exposure is the greatest danger in combat. His solution, the elevating pod, was an attempt to mitigate that risk. Where Tapp failed was in the execution. He tried to solve the problem by putting the human operator inside the elevated section. This introduced the physiological and ergonomic nightmares that doomed the project. The technology of the 1940s simply didn't exist to separate the human from the machine. There were no cameras, no fiber optics, no reliable remote controls. To aim a gun, you had to look down the barrel. To look down the barrel, you had to be there. So, in a sense, Tapp wasn't wrong about the problem. He was just limited by the tools available to solve it. He built a mechanical solution to a biological problem, and biology won. 9. Strategic Engineering Lessons. Deep Analysis Section. The story of the Praying Mantis offers several profound lessons for engineers and strategists. First, there is the risk of trauma-driven innovation. Tapp was motivated by his personal experience in the trenches of World War I. He wanted to save lives by preventing the kind of deaths he had witnessed. This emotional drive is powerful, but it can also be blinding. It can lead an inventor to focus obsessively on a specific problem, in this case, vertical exposure, while ignoring the broader context of how warfare is evolving. Tapp solved the sniper problem of 1916, but he missed the maneuver warfare revolution of 1944. Second, there is the clash between engineering arrogance and biological reality. Machines obey the laws of physics. They can be built to withstand immense forces, lift heavy loads, and operate in extreme conditions. Humans obey the laws of physiology. We get tired. We get motion sick. Our blood pools when we are tilted. Tapp designed a machine that worked on paper, but failed because it ignored the limits of the human body. He treated the operator as just another component, rather than the most critical and fragile part of the system. Third, there is the danger of over-specialization. The praying mantis was a highly specialized tool. It was brilliant at one thing, firing from cover, but terrible at everything else. In warfare, flexibility is often more valuable than perfection. A general-purpose tank like the Sherman or the T-34 could do many things well enough. Fight other tanks, support infantry, exploit breakthroughs. The Mantis could only do one thing, and even then, only under specific conditions. When the war didn't match those conditions, the machine became useless. Finally, there is the issue of technology lag versus doctrine speed. War evolves faster than individual obsession. While Tapp spent years perfecting his mechanical insect, the German army was rewriting the rules of combat with blitzkrieg. By the time the Mantis was ready for testing, the doctrine it was designed for had been obsolete for decades. The praying mantis is not alone in the graveyard of military inventions. World War II saw many experimental vehicles that failed for similar reasons. The Maus super heavy tank, the Panjandrum rocket-propelled wheel, the various land battleship concepts. Some weird ideas succeeded because they solved a relevant problem. The DD swimming tanks allowed armor to land on D-Day beaches. The Hobart's funnies cleared obstacles. These were specialized, yes, but they were specialized for the current war. The failures, like the Mantis, often suffered from what we might call evolutionary dead branches. In the brutal Darwinism of military technology, survival depends on efficiency and adaptability. Traits that don't contribute to victory are ruthlessly eliminated. The praying mantis was an evolutionary dead end. It was a fascinating mutation, but one that couldn't survive in the environment of 1944. Ernest Tapp spent 7 years chasing a memory. He poured his time, his genius, and his hope into a machine he believed would save soldiers from the fate of his friends in the trenches. When the project was canceled, it must have been a bitter blow. But the praying mantis did not fail because it was ridiculous. It failed because war had changed shape. Tapp built a perfect answer to a question that history had stopped asking. The danger in military design is not bad engineering. Tapp was a brilliant engineer. The danger is outdated imagination. Every war builds weapons to defeat the last war. We prepare for the Somme and get the blitzkrieg. We prepare for tank battles and get insurgents with IEDs. The praying mantis stands today in the Bovington Tank Museum, a strange, silent sentinel. It is a monument to ingenuity, to trauma, and to the relentless march of time. It reminds us that even the most brilliant ideas can be wrong if they are solving the wrong problem. And perhaps, in its strange insect-like form, it carries a warning. Beware of fighting ghosts. Because while you are busy building a shield against the past, the future is already arming itself with something new. History is full of what-ifs and near misses. The praying mantis is one of the most poignant. It represents a noble failure, an attempt to save lives that was doomed by the very progress of the war it sought to influence. It challenges us to look at our own creations and ask, are we solving the problems of today, or are we just fixing the traumas of yesterday? Are we building tools for the future, or monuments to the past? Thank you for spending part of your day with us to explore this fascinating chapter of military history. If this story of engineering, memory, and the changing face of war resonated with you, we'd be honored to have you with us again.